You probably know that quantum gravity theory, or the theory of unified field, or the theory of everything, is how it's also called, is basically the holy grail of all modern theoretical physics. That's a theory which even Einstein wasn't able to build. But here is one problem with it. Look, if I just Google it, the naive energy scale at which quantum gravity effects become relevant is like 10 to the power 19 gigaelectron volts, which is around like a quadrillion times higher than we could measure on LHC. So one could naturally ask, is this it? Are we kind of done with quantum gravity theory? It should righteously earn the status of the most useless theory in the world because we would never be able to measure something like this. I remember somebody ran an estimate that it will require like a collider the size of the galaxy to get to this level of energies. And this was already ridiculous enough, but then somebody found a mistake in this calculation, and it turned out that it will require collider the size of the all observable universe to reach these energies. So, which made it, even slightly more unlikely to ever be observed. So that begs the question: why are we even trying to build this theory? Now, for me, it was always something like, well, yeah, maybe we couldn't measure it like this, but let's just try to build it. Maybe it will reveal some sort of inconsistencies with our previous knowledge, just the whole attempt of it. And maybe it will lead to a breakthrough in theoretical physics and open up new horizons for new understanding, which then give us hints to new type of experiments which we could perform, and then we will discover new theories. That's how I thought about it. It quantum gravity certainly is important somewhere in the middle of, at the center of the black holes. It certainly probably was important, at least at the beginning of the universe. So we could have a glimpse into it from there, and hoping that these hints allow us to go further. That was kind of my perspective, at least up until recently. And I wasn't, it wasn't really studying this topic that hard because the hope is really small that we can get anything out of it. And now when I was preparing this video, I actually did a little bit of research, and it turned out that some people actually hope to see quantum gravity directly on LHC, even in this kind of simple, what's called effective field theory paradigm, where our energy scale, quantum gravity energy scale, determined by the Planck's mass. However, the assumptions are quite unnatural. In this particular paper, for example, they assume that the Planck's mass as a coupling constant receive quantum corrections, and in certain circumstances, these quantum corrections can reduce this gravity coupling constant, the Planck mass, this 10 to the power 19 gigaelectron volts, to something more realistic. However, it requires the existence of a hidden dark sector which has like 10 to the power 33 different particle species. So imagine it's like if you have like an electron, yeah, then you have another particle, let's say called electron number 2, electron number 3, electron number 4, and then like this somewhere to 10 to the power 33. So then this is the formula which determines the effective Planck's mass. And as you can see, the calculated n is that big. This effective Planck's mass will be around TeV, which is what we could measure. Yeah, I don't know. For me, it's not convincing, right? It seems extremely unnatural. So this paper doesn't actually give me much hope to see it on the collider. Another approach which I found, that's a paper by Nimar Hani Hamed, Dimopoulos and Dvali. I don't know this person, but there are similar ideas coming from WAFA these days. It is extra dimensions. Again, there's nothing really new, right? The paper is 1998. It just states that if you have relatively large extra dimensions, the law of gravity will be modified. We will not have a 1 over r square, attracting force between two gravitational objects. It will be 1 over r to higher power, and we will be able to measure this deviation just from very precise experiments in the lab. So yeah, but that hasn't been confirmed yet. Plus, again, I don't know whether you found this idea of extra dimension anyhow, pleasant or favorable, because it's also kind of arbitrary and artificial. So that doesn't really excite me. And I kind of was already thinking to give up on the whole, hope of finding quantum gravity anywhere at reasonable scales up until recently, where I just accidentally attended a talk by this person, Laurent Friedel. I don't know how to pronounce his name. And it was actually dedicated to like his own research. But in a discussion, he explained to me that, well, actually, if you believe in holographic principle, that implies what's called UV-IR mixing, and this would potentially allow quantum gravity to pop up on much low energy scales. So let me explain you what UV-IR mixing is and how it appears in holographic principles. But at first, let me remind you what the holographic principle is. So you probably know this whole story with Bekenstein and then Hawking calculation of the entropy of the black hole. And the striking feature of this calculation or result that they got is that this entropy is proportional to the horizon area. In other words, proportional to the volume. Not proportional to the volume, as you would expect, proportional to the area. So it's kind of weird, right? That's not how most objects behave. From there, they were able to obtain a bound on the entropy of any system in terms of the area of the region which it occupies. Like there is some sort of hand-wavy argument in terms of like, well, if you put too much energy into this area, it will become a black hole, and then we know the entropy. It will be the entropy coming from the horizon, and then we know it's basically maximum possible entropy, because you can't extract anything out of a black hole, this kind of sense. So that gives us some sort of hint or clue, or prompts the hypothesis that the entropy of quantum fields in any region which interacts with gravity is proportional to the area. But that by itself means that it could not be described by just simple local degrees of freedom who live just here and interact at small distances. And this means that the physics at small distances could be affected by something happening at large scales, and vice versa. That's what's called this UV-IR mixing. And indeed, let me show you a paper where people even were able to obtain a certain bound on like dark energy from these considerations. This is actually a review of this result. Let me just read. In doing so, we'll adopt a popular example of UV-IR mixing that has received increased attention recently as a guiding principle, the Cohen-Kaplan-Nelson CKN bound on quantum corrections contributing to the dark energy density in the universe. The argument is based on the well-known observation that the quantum field theory has a limited range of validity bounded by a UV cutoff lambda. Okay, this is, we know, it's a standard QFT. An upper bound for this cutoff can be estimated as an energy beyond which quantum gravitational effects allow for the production of black holes. As these black holes will increase in size with high energy, hence high energies won't correspond to probing small distances anymore. Yeah, that's a kind of hand-wavy way of saying it. Cohen, Kaplan, and Nelson then argued that this UV bound should be complemented with the IR cutoff originating from arguments about black hole entropy. In fact, according to black hole thermodynamics, the maximum information in a box of volume L to the power 3, L cube, scales as the surface area of the box, L squared, instead of extensively L cube, as would be expected in a conventional field theory. This implies that there must be a maximum length beyond which quantum field theories vastly overcount the degrees of freedom of the fundamental theory. Yeah, that's what I was trying to say in this about this holographic principle. That with gravity, somehow the QFT degrees of freedom kind of cancel out in a weird way, but nobody really knows how it works. So CKN obtained an even more stringent bound for the IR cutoff, lambda LIR, by requiring that the Schwarzschild radius of the maximum energy configuration, which is L cubed lambda to the power 4, stored in the box, should not exceed the size of the box. Yeah. And from here you see they found that infrared cutoff, the size of the box, is expressed in terms of UV cutoff. This expression constitutes a relationship between the IR and UV cutoffs, according to which the IR cutoff, LIR, scales with the inverse squared of the V cutoff, lambda. CKN go on and adopt as the IR cutoff the present horizon size of the universe, obtaining a V cutoff of 10 to the power minus 2.5 eV. That is surprisingly close to the observed value of the cosmological constant. So yeah, you see, you might say it's like the first really good prediction of cosmological constant, because this means that for the size of the observable universe, the size of this vacuum energy is the smallest possible energy, in a sense, that could not sustain any quantum correction. Yeah. Yeah, protects dark energy density from quantum corrections. Yeah, so that's kind of points in a direction that this holographic principle can be true. But what does it mean, like for us as humans? How exactly we would see this kind of quantum gravity effects, which now kind of appear non-locally, or how they manifest themselves? And I don't know If you just Google what kind of toy models of quantum field theories have UV-IR mixing, the simplest one would be the so-called non-commutative QFT, non-commutative quantum field theories, which are kind of inspired by string theory, at least in the form which people usually study them. Yes, the idea goes as follows. We promote coordinates x mu x nu or Lorentzian manifold to this kind of operators, which commute on some new tensor, theta mu. And again, that's just the simplest possible non-commutativity. Of course, you could study something more complicated, but that's how it appeared in string theory. And then we study quantum field theory on this space. We need to introduce a new non-commutative product on function such that f star g minus g star f would reproduce this for coordinate functions. And we could write down Lagrangians. So yeah, in this paper they studied scalar and Fermat theories. Yes, there is this standard lambda phi to the 4 theory. And they solve it at one loop, using just Feynman diagrams. The novelty is now that non-planar diagrams give new type of contributions with this phase factor depending on theta. Let me show you what the results are, because it's kind of interesting, quite intriguing. Here they perform smooth Schwinger regularization, express propagator in terms of proper time, add this cutoff to the integrands of lambda, lambda is the V cutoff, and then calculate the answer for planar and non-planar diagrams. In the non-planar diagram, this new scale appears, which depends on this weird norm of momenta, p, which depends on theta square and the usual cutoff. And they calculate the effective propagator or an effective action. So what's curious here is that if you look at this expression, depending on whether lambda is sent to infinity or not, the small p limit of this expression is very different. For any fixed lambda, finite lambda, there is no IR divergence. Yeah, p could be put to 0 with no problem. But when lambda is sent to infinity, then p could not be 0. That's how this UV-IR mixing manifests itself. The UV and IR limits don't commute. And they interpret it as an extra particle because it's an extra pole in the propagator. And the authors attempted to even find the corresponding action. But it looks somewhat weird. First of all, they were not able to cancel logarithmic term. I don't know why they just ignore it. But the action is kind of bizarre. It's this new scalar high. And it's not clear whether it's physical or not. So it's hard to imagine how we would see this kind of field because it has non-standard kinetic term. It seems like it directly violates Lorentz invariance. Yeah, as you can see. explicit Lorentz validating. But the other question, is this bad? Is this actually something wrong? Because isn't UV-IR mixing implies that Lorentz invariance no longer holds, and we could have interactions on a distances, on a space like in a space like separated over space like separated regions. Well, how do you call it? I forgot the right term. We can violates, no faster than speed of light travel or something like that. I don't know. It seems kind of unphysical. Should we just abandon this theory immediately or what? Because in some sense, even in like more conventional quantum gravity theories, like what follows from string theory, Minkowski space is just one vacuum solution of string theory. So all our standard properties of homogeneous isotropic spacetime, they just the property of a particular solution, they just emergent. So speed of light is emergent in all these things. They valid in this particular Minkowski space. So maybe we should not really hold them too dearly. I don't know. So it kind of begs the question, like how speed of light or how notion of time even should work in quantum gravity. If we sum in all metrics, some metrics might not have a preferred time coordinate or the notion of speed of light. So I don't know what to make out of it. Okay, I guess that's all I was want to say today. I don't know whether you're interested in exploring this kind of UV-IR mixing further and how to make it intuitive. Like, is this just extra particle with extremely weird kinematics just pop out and out of nowhere for arbitrary energy scale, or it's something else. So I don't know how to visualize it, and when could you expect a discovery. But at least we have some hope that we can see some progress in our lifetime if we just don't think only in terms of colliders.